Okay, dear students, we talked about postulates of we are talking about postulates of quantum mechanics. In the previous lectures, I talked about postulate 1, that was about the wave function. Okay, we talked about in details what is the wave function, what is its physical significance, what is Born interpretation, what are the properties of a well-behaved wave functions. Then I talked about normalization procedure, normalization of the wave functions, orthogonality, orthonormal wave functions. I also talked about the wave functions uh, properties in terms of shape, that what will be the curvature of the wave functions, whether it will be a positive curvature or a negative curvature, that can be qualitatively determined from the Schrodinger wave equation. This was the point where I left you in the last class. So we talked about postulates 1 in the previous class. Today I will talk about postulate 2. And postulate 2 is about the operators. Postulate 1 was about wave function, postulate 2 is about operators. We say that operators are symbols for a mathematical operations. All are multiplication symbol, addition symbol, division symbol, okay, differentiation, integration, all are symbols which in itself has no meaning unless you have a function. So if you write ddx of x cube, then it means you are differentiating with respect to x to a function x cube, and the function changes to 3x square. That you know. In the same fashion, in quantum mechanics, we have operators represented by symbol, either this circumflex on the A or a tilde on the C. This cap, which we normally say cap, is actually called circumflex, or this symbol is called tilde. In certain cases, you will find in certain books you will find an arrow also on the function, on the operator symbol. So this indicates a specific types of mathematical operations. Okay. These operators, when you operate with an operator on a function in a quantum mechanics, then there is two possibility. One is that the function itself changes to a new function, or another is that you get the same function back multiplied by a constant, say d, where d is a constant. Both possibility exist in quantum mechanics. So either you get this one or you get this one. And so we will talk about the difference between the two later on, but for the time being, these operators operate on a function and give you a new function, or when you operate with an operator on a function, then you get the same function back multiplied by a constant. And what is the function in quantum mechanics? It's the wave function. So fx is always in a quantum mechanics a wave function. And what is wave function? I talked about. Wave function is a mathematical function. So I talked about it in the previous class. It's a mathematical function. So you do an operation of mathematical operation on a mathematical function in quantum mechanics. Okay. So if you have in quantum mechanics, for every physical variables there is a corresponding operator. So for every physical variable, we have a corresponding operator in quantum mechanics. If you write for one of the physical variable I am writing, it is position. So, position has a operator. If I write x component of momentum represented by a symbol px, this is represented by a symbol x, it has a moment, it has a operator. So, corresponding to position we have an operator x, and corresponding to momentum in quantum mechanics we have an operator minus I h cross d dx. I do not know whether I have written it or not. H cross is actually h divided by 2 pi. Okay. So, these two operators I have written for a x component of momentum and for position. When it is written, so in order to set a operator for a particular physical variables, you need to represent that physical variable in terms of coordinates and momentum. So, for any physical variable, if you want to know the operators, then you represent this physical variable, represent it in terms of, I would write in terms of coordinate and momentum. And then use the operator of position and momentum. Okay. So, for example, if I write kinetic energy, and all of you know the kinetic energy is classically it is 1 by 2 mv square, which you can write as m square v square divided by 2 m, and which will be 2 p divided by 2 m, sorry, p square divided by 2 m. So, for x component of kinetic energy, you can write px square divided by 2 m. Okay. Now, you have already the operator of x component of momentum. So, use this one and you see how can you use it. So, px is minus I h cross square d dx. So, what will be the square? Px square will be minus square if you do plus, and then it will be I square, sorry, it is not a square, I h cross d dx. Okay. Let me check. Yes, I h cross. Okay. So, it will be I cross square h square d square by dx square, and I square is what? Minus 1. So, it will be minus h cross square d square by dx square. So, I will write kinetic energy x component will be minus h cross square d square by dx square divided by 2m, or you write minus h cross square divided by 2m d square by dx square. So, this is an operator for kinetic energy, or better to write x component of kinetic energy. We can say, okay, or if you open it up, it will be minus h square divided by 8 pi square m d square by dx square, and this you have already done while doing the derivation of Schrodinger wave equation. This is called Hamiltonian operator. Okay. So we got the operator for x component of kinetic energy by simply using the operator for momentum. Okay. So you can write the operator for y component and z component also in the same fashion. It will remain same. So it is y component of the momentum then it will be minus I h cross d by dy. Z component of momentum will be minus I h cross d by dz and so on. Same way for momentum, and for energy minus h cross square divided by 2m d square by dy square, and z component will be dz square. Okay. So same way you can write, and if you have the total kinetic energy, then it will be common to everyone, minus h cross square divided by 2m d square by dx square plus d square by dy square plus d square by dz square, and this you know we can write as where del square is actually another operator which is called, we did in the previous derivation of Schrodinger wave equation, we did this one. This is called Laplacian operator. Okay, and this is called Hamiltonian operator, total kinetic energy. Okay. If I say potential energy, for potential energy we give a symbol V for the potential energy, and this potential energy depends upon your system, that how the system is interacting. Okay. If you have an electron and if you have a nucleus like in hydrogen atom, then the potential energy between these two is minus E square by R. Okay. If you have a simple harmonic oscillator, then the potential energy is 1 by 2 k into x square. Okay. So these potential energies terms are used as such. So if you have total energy, then total energy is kinetic energy plus potential energy. So you can write minus h cross square divided by 2m del square plus V, and we say this is the operator for total energy. And what kind of operation is this one? Operation is double differentiation, d square by dx square, d square by dy square, d square by dz square. Okay. And if for position I said you the operator is x, means simple multiplication by x, nothing else. Okay. So, for a y component it will be like this one, for a z component it will be this one, for a radial system it will be this one. So, all these are multiplication by y, multiplication by z, multiplication by r, and so on. Okay. So, in order to get the operator for a particular physical variable of the classical mechanics, you need to write that variable in terms of coordinate and momentum, and then use the operator for coordinate, operator for position, and operator for momentum, and you will get the new operator for the new physical variables. Okay. We got the operator for physical variables and corresponding operator. In every quantum chemistry book you will find a table like this one, that for position x you have an operator x, for x component of momentum, which is represented as px, you have an operator minus I h cross d dx. For x component of kinetic energy, you will have an operator like minus h cross square divided by 2m d square by dx square. For potential energy, V, and if it is the x component I will write V. So, this we write V symbol only. Okay. Total energy, we can write minus h cross square divided by 2m d square by dx square plus V. So, this is for one dimension, and we can add other dimension also depending upon the system. Okay. We can write in the same way the angular momentum. Angular momentum is what? Angular momentum is mass into velocity into radius, mvr, and mv is what? Mv is linear momentum. So, again you can write in terms of coordinate and momentum, and you can find the value. We will knowingly I am not writing right now, because angular momentum chapter we do have, and we will be covering it up again in details. So, here I am not writing. So, all these operators you will find in any quantum chemistry book. So, here you have single differentiation, here you operation, mathematical operation is multiplication by x, one time differentiation, two time differentiation, and this depends upon what is the relation for the potential energy. Okay. Now, there is certain rules in quantum mechanics for playing with these operators, and those rules are called algebra of operator. It is exactly like number algebra, which you already know. So, what is the algebra of operator, we will see. Okay. In algebra of operators, we talk about that how, if we add two operators, what will happen? If you multiply two operators, what will happen? Okay. So, let us talk about addition and subtraction. Addition and subtraction. If you add two operators A plus B, then you get a new operator. you have two operators, A and B, and if you add these two together, you get a new operator, or if you subtract this, then also you get a new operator. And if you operate with this operator on a function f(x), then what you get? Like this one. So the operation means operation of with A on function f(x), and then operate with function B on the function f(x), and then add these together. This is called addition and subtraction of operator. Okay, and examples you can write that if you have A is equal to d dx and B is equal to x, then you operate with this operator d dx plus x on a function f(x), and what you should get? It should be equal to d dx of x(x) plus x into f(x), multiplication by x. Okay. So this way we can talk about many different variations of this addition and subtractions. You can take a specific mathematical function and you can check whether you get it or not. So addition of subtractions leads to a new operator with which you can operate on a function. Okay. Then if you multiply operators, what about the multiplication of operators? If you have operator A and operator B and you multiply them, means you write A B multiplication and you operate with a function f(x), then what does it mean? It means that you will operate with function operator B on function f(x) and you will convert this into gx, and then you will operate with operator A, and that will be g prime x. Means multiplication of operator gives a new operator in which you have to operate in a particular direction from right to left. So mathematical operations is from right to left. Okay. So this is fixed. You operate with an operator which is closest to the function first, and then go to the next operation. So if you have A, B and C, three operators, and if you write operate with function, then it will be sequentially. Then you have Qx and then you have Qx prime. So this is operation by C operator, and this is operation by B operator, and then you operation by A operator. So sequential multiplication of operator tells you the sequence of operation by from left to sequence of operation. It defines the sequence of operation. Okay. If all are different, A, B and C, if it is not so, means if you have A square, if you have A cube, okay, then operating with same operator, same operator twice. Operating with same operator thrice, and so on. So this is what an operator, the square of an operator means. Okay, squaring an operator, or giving a power cube to the operator. Okay, so we talked about addition, subtraction, and multiplication of operators. Okay. Now, if your operator is, what is your unitary operator? Is an operator 1, symbol this one. Multiplying by 1 is a unitary operator. Multiplying by 0 is a null operator. These are the terminologies which you should know. 0 operator. Okay. Then the next thing is that operators show associative law. Okay, what does it mean? A, B, and C must be equal to A, B into C. Okay. Associative law. So operators obey associative law of multiplication. Law of multiplication. This is also important. Okay. Now, the major difference between the number algebra and the operator algebra is that when you operate with two operators A and B on a function fx, let me write it. If you operate with two operators A and B on a function fx, and then you operate with the multiplication like this one, B and A, then you may get the equal result and you may not get the equal result. In number algebra, if you multiply 2 by 3, you get 6, and if you multiply 3 by 2, then also you get the 6. But in case of AB, may not be equal to, may be or may not be equal to BA. Both possibility exist. May be equal, may not be equal. If they are not equal, if AB is not equal to BA, then what you can define is a quantity AB minus BA, and this is represented as a symbol A B within this bracket, and this is called commutator. Okay. So this is the major difference between number algebra and operator algebra. If you multiply, then this two may be equal, may not be equal, and thereby the difference between the two operations is given a symbol commutators. And this is very significant, very important in quantum mechanics, this commutator. Okay. So these are the laws of operator algebra in general, and then we can talk about, we talked about the square of an operator, we talked about the cube of an operator, we talked about the multiplication, we talked about the commutators of an algebra. And then we will talk about further on the examples of these and find out we will try to find out the commutator of two operators, position and velocity, and we will see whether they commute or not. If they commute, we say if A and B is equal to B into A, we say they commute with each other. Commute with each other. And if A and B is not equal to, we say do not commute with each other. In the next class, we will see the examples that whether the position and the velocity, position and the momentum operators commute with each other or not. Okay. So in the next class, we will start from this point.